tonight, who is both a friend and a colleague from CU's astronomy department. And everybody here, I know Explorers Club personality types. Everybody has seen like the wonderful pictures from Hubble, but the pictures are overrated, okay? The Hubble telescope carries a number of instruments, and the ones that really matter are the spectroscopes, okay? A spectroscope doesn't make a pretty picture, but what it does is it takes the light and it breaks it up into all the colors of whatever rainbow is present. And when you study the spectrum really closely, you can tell what stuff is made of. You can tell how hot it is. You can tell how it's moving. Is it got a red shift and moving away from you, or a blue shifter coming toward you? Is all that gas falling into a galaxy or being blown out of a galaxy? So all the stuff that we really learn and understand about what's out there in space comes from the spectroscopes. And Jim has spent pretty much his whole career inventing spectroscope after spectroscope. And the most, notable, that's the right adjective exactly, spectroscope on Hubble, used by hundreds of astronomers to make all kinds of discoveries, is something that he invented. And for those of you connected to Ball Aerospace here in town, is that true on cost?
COS was a joint CU Ball. Right.
And Ball, did construction of it. The other thing that I think you'll find pretty interesting is that Jim has worked a lot with what are called sounding rockets. And sounding rockets are these cute little small rockets. They're small enough they would fit in this room, and they get launched into space and they go up. They're very much, I would say, like Blue Origin. You go up into space and you're there about 10 minutes, give or take. 5 minutes. But you're there in space, and you can see things and you can do things that you could never do on the ground. And then that little rocket parachutes its payload back down, and you go and get it. So it's all really, really cool instrumentation stuff. And I bet he's going to tell you all the interesting details. So please welcome Jim Green.
Well, now I don't have to explain sounding rockets, which is where I'm going to start the talk, but that's okay. So today's talk was entitled Space Telescopes, Little, Big, Biggest, and on the left there, that is a sounding rocket. That's little, and I'm going to talk about those. Then I'm going to talk about big, Hubble, and then finally biggest, James Webb Space Telescope. So I'm going to take this from an instrumentation point of view, and I will touch on some of the science issues that we do and stuff like that. But this is rather informal, so by all means, don't hesitate to interrupt if you have a question or you want further explanation of anything I'm talking about, because I'm a professor, and if you get me started, the problem is getting me stopped, not getting me to keep going. So sounding rockets, which, as Doug mentioned, I did one for my thesis originally in 1987, and including that one, I've launched over 20 sounding rockets during my career. I believe I'm, for astronomy, at the top of the list there in terms of numbers. But typically these are about 0.4 to 0.5 meters in diameter telescopes.
24 to 25 inches, you meant to say, right?
No, diameter. We work in MKS. This is actually, it really should be centimeters because it should be CGS, right? But physicists do CGS and engineers do MKS. But this is sort of the size we like to work with. Here it's because we have either 17 or 20-inch skins to work with, 22-inch skins. Now, I just put up one slide to mention the even smaller telescopes, in case you're unaware, are called CubeSats. This is actually a CubeSat that was built at CU by one of my colleagues, Kevin France. It's now orbiting the Earth and doing science by studying the atmospheres of planets that are orbiting other stars. It's called the Colorado Ultraviolet Telescope Experiment, CUTE. And this was the sticker. We always make a sticker for every mission. And I put this picture in so you can really get an idea of the size. They're only about this big, so the aperture here we're talking about is measured in single-digit inches, 3 inches, 4-inch apertures. So they usually have very, very specific science objectives that haven't been addressed in some other ways. But I'm not going to talk about CubeSats because I don't do CubeSats. I will talk about sounding rockets. So here's the little picture to go with what Doug was explaining. We launch, and I'll show some launch videos. The rocket is provided by NASA. One is surplus military, the booster. The other is actually made by a Canadian firm, the sustainer. We kick off the nose cone. We don't deploy booms. Those are for people who do heliophysics. We then point at the star or the galaxy we're interested in. We have a live telemetry link to it. We usually stay about 300 seconds in space to do our experiment. Then it comes down and usually the parachute opens. I've had 3 of the 20 I've launched. 2, the parachute failed, and 1 we had to destroy because it had a guidance failure, was headed straight for Phoenix, and we blew it up. And that parachute opened but didn't really work. One of the exciting parts is the attitude control system isn't by itself good enough actually to acquire the target. So after it gets us close, the graduate student involved has to actually, with joysticks, make the last acquisition to put the target onto the entrance aperture of your spectrograph. We usually allot them 10 seconds for that job. I always am standing behind them to push them out of the way if they go into a panic. That's never actually happened. As an exciting part, on my thesis launch, the camera that was supposed to show me where the star was relative to where I wanted to put it failed, and so I had to do a blind spiral search, which succeeded. I found it after 27 steps in my spiral search, which in those days I had to enter by a button. I had to push in the button and say execute, button, execute, and I did get my data and thesis, but that was the longest 110 seconds of my life.
I don't know if it's too much detail, but I think most people are more familiar with the launches of large rockets.
Yes. I'm going to show a launch. So it's like a giant model rocket. It goes boom and it's gone. It does not majestically rise through the air. We hit Mach 1 in about 6 seconds, and we hit Mach 5 a little while. The sustainer will burn out at about 100,000 feet, and then it will coast all the way up to almost 200 miles. So then it comes down in the desert. Here is an example of finding it the next morning and checking it out. And then we put it on a helicopter. This is an old picture. And fly it back.
You can do that?
Well, I don't get to fly it. Yeah, you can do that. This is great. So you can see somebody there. We sit in the back. These were when we did it with Hueys. We use Blackhawks now. But I always fought to get to the gunner's seat. There's no gun anymore, but you are just sitting there out doing 140 miles an hour in the early morning in the desert. It's actually really cool. So I have lots of stories about the helicopters and landing in an unexploded bomb field, and the time we actually went over and flew over I-25 on the other side of the mountains. And I said, why are we going this way? They said, oh, they're launching some radar-homing anti-aircraft missiles, and I thought we ought to be on the other side of the mountains. So I told them that I agreed with that theory. It can be fun. There's a lot of adventures that go on with this. So I'm going to show the video in just a minute, but this is sort of what you're seeing here. So this is not ours. So there's a sustainer that burns up very quickly. These are actually the boosters that are used to launch cruise missiles off of Navy missions. The Navy decides they're not reliable enough, so they give them to us for free. It separates out just by air resistance. There's just some plates on here to create air force. And then the second stage lights, and most of the work comes out of that one. That'll burn. This will burn for about 4 or 5 seconds. There's a few seconds to separate. Typically, this ignites at about 12 seconds and burns for 30 seconds. Now I'll show a really cool video, which is what I'm going to show right now. If I can get this, come on. There you go. Play nice with me. But the way it's doing...
I don't think you've told us where you launched from.
So these launches typically occur at White Sands Missile Range, which is down in New Mexico. So we live in Las Cruces. I think I have accumulated 1 year of living in Las Cruces with 20 launches. And I know I still haven't been to every Mexican restaurant in Las Cruces. But I think I know which are the best ones. We launch at night, and I will show a night launch video in just a minute. This is a day launch. This is we have colleagues. There are multiple sounding rocket programs at CU. One of them is run by Tom Woods, who does solar physics. So he launches in the day. And so he has onboard cameras, and that's what I'm going to show you here. So if you look here, here's the countdown clock, -6, -5. Here's the speed. Here's the G's. We're at 1 G because we're on the ground. This is looking down. Here we are launching. First stage is burned out about now. Second stage is going now. So we're slowing down from air resistance. That's why the G's are negative. Now we light up. And we are starting to cook. Okay, that's meters per second, right? If you want meters per hour, you need to multiply by 3,600. 5 G's. 6 G's we're spinning to stabilize currently. The fins are canted to give the stabilization. We'll peak out at about 8 G's. Maybe a little more. Depends on the payload. Here is our flight profile. You can see the rocket climbing up. Okay. Now we're going to despin. We send out 2 weights. A cable with 2 weights wrapped around in the opposite direction. You cut the ties, and that despins it. So we're done. We're at 0 G. So in a second, it will, in about a minute in, usually about 60 seconds. Depends on the flight profile.
That sounds kind of MacGyverish. You just throw out 2 weights?
2 weights tied to the cable that unwrap it, and you set the weights and the length such that it won't quite do the whole, there you go, bang. And you might even see the parts flying off. So this is switched with their one window. There go some of the pieces. And then the gas jets on board will do the rest. So here we are. The Earth is definitely round.
Cold gas?
It's cold gas jets, yeah. So we used to use Freon. That's not allowed anymore. Those are the O-ring. Those were the rings that held the separation stage on it. It'll pop that off. That's the door. And they're going to now maneuver to point to the sun. And there's the sun. And now it gets boring. It's just going to stare there and actually do science. But so we're about 2 minutes in to the flight, and we'll go another about 5 minutes of taking data, and then we'll start to re-enter. Now this video goes all the way, and I can give you the link if you want to watch it all the way to go opening. It takes about 20 minutes to hit the ground. 15 minutes of that is just on the parachute. Okay.
When you launch, do you point at the azimuth at launch, or do you roll towards the azimuth?
Okay, so that's a little complicated, but I can explain it. So we typically, these are missiles, not rockets, because they have guidance, so we have fins in the front, and so we try to adjust for the wind, and we want to launch downrange. We want to land downrange, so the actual launcher points downrange, and then slightly left or right. We nominally launch due north, but because we do a curveball in the wind, and sometimes when I launched in '87, they were actually rockets, so we had to actually calculate that. So we need the wind profile for the whole night, so we launch balloons every 30 minutes, little Mylar balloons, and track them on radar. We lost a launch one night because we don't track them on radar anymore. We put little GPS transmitters on them. It's great. Right at midnight, all our balloons turned off. And it turns out, because we were using the military GPS for precision, they changed the encryption and didn't tell us. And
You're going above 60,000 feet?
we're going to 200 miles. Yeah. Yeah, but the wind is only, we don't care about we only care about the wind at the low levels. The first 100 feet, we have towers measuring the winds. And if the wind is too high, we don't launch. And if there's lightning in the area, we don't launch. But I'll show you a little more of that. Yeah, people like that video. So I'm just going to have to go through these real quick, but that's okay. So I'm going to go through now an actual payload we built. I said telescope, so this is actually a grazing incidence telescope. So this is the outside, the surface is on the inside. This works in the extreme ultraviolet where the reflectivities are very low, but if you come into grazing incidence, you can reflect X-rays. It's actually, it's a parabola and a hyperbola. So if those of you know a Cassegrain telescope, this is the grazing incidence analog to a Cassegrain telescope. It's called a Wolter Schwarzschild 2. We machined this. This actually flew first in 1987. to look at supernova A7A before I was even here. And this flight will be its 7th that I'm going to be talking about. It's been in space. When I came to CU in '89, they were having problems with this, and I was actually hired by the PI of this program to get it, whip it into shape. So I built them a new detector and fixed everything. And well, that was the beginning of all the stuff. This is the detector we use. When we launched it, it was the largest microchannel plate to ever go into space, part of the tech dev we do on these missions. So this is 8 inches square. And this counts photons individually. Each photon as it arrives stimulates the detector. We record its position and the time of its arrival. And we don't make a picture, we just get a list of each photon, where it hit the detector and when it arrived, and then we can make that data into a spectrum and stuff as we go on. This is all done in clean rooms because of contamination. That's purging nitrogen over the face because the photocathode on there that reacts to the photons is susceptible to humidity degradation. Yeah, go ahead. No, one of the advantages of these is they operate at room temperature. It's not cryogenic. Here it is mounted into the skin of the payload, so this is just the back end. You might have noticed it's purple. In an earlier flight, we coated that with silicon carbide for reasons I won't go into long distance, but we can't get it off. It's there forever now. And then here's the back end that this will match to that piece. And then the grating that disperses the light lives here, and the detector mounts to this plate. We keep this under vacuum at all times that we aren't actually working on it to keep it clean. So this is the vacuum pump that's almost always attached to it. In fact, is attached to, we only detach it from it at T-3 hours out on the rail. Now when we put it together, we go to NASA. So this part is what we built. This is the telemetry units, the guidance, the attitude control system, and the things, the parachute stuffed under the, it's in this section here underneath the nose cone, and the part that did the D-spin and stuff like that and ignites the second stage is here. So NASA provides that part, we build this part, and then we'll put the engines on when we actually get to White Sands Missile Range. Once it's there, here are the engines. This is the booster, that's the sustainer, and there's the payload. This is, this will raise and lower and is on a pivot. This is actually a turret from a battleship, same design that they use. Now there's a building that goes over in this on these rails, which we can pull off and put it over it and drag it over when we want. This is not actually, this photo was the best one I could find. This is from a different launch, but this is typical. We always take this photo. This is Carrie Hoadley's thesis. She's now a professor at the University of Iowa. And Kevin France was the PI here, and these are other grad students, engineers, postdocs, and then the NASA guys to get this photo. Give you an idea of the size. It's about 50 feet tall. So it would be close to fitting in here. Here it is on the rail inside the building. Like I said, it's on wheels, and we pull it off for launch night. You can see the vacuum pump and system is here. We put this styrofoam box around it to control the temperature and get the balance. And everything that's red is removed before flight because all these things have pyrotechnic activation. And there are safety bands on them so they don't fire while you're in there because that would hurt a lot. And so on the night we pull the building back, we erect the launcher and push the button. So I'll show you a night launch here. Come on. Come on, show me this. Yes.
What's the engine burn?
I'm sorry, what?
What is the engine burn?
It's solid fuel, both of them. If you really want the chemical composition, I could get into it, but it's okay.
But it's a solid fuel.
And these are both solid fuel engines. Once you light it, they're gone. Let's see, I want about 250. This is close enough. Not on these. So I don't know exactly where my volume is gone. Let's see if I get any sound out of here. But it's going to launch in a second. You'll see, and it's going to go through the clouds. It's pretty cool. This is the track. We have lots of high-speed cameras on it for the launch. Some are static, some track. This is a tracking launch.
Why do you do it at night?
Well, we want it because the sun is bad. That's noise to us, as is the northern lights, which I'll mention when we launch. So there's the launch, and there's the clouds. We think that's pretty cool. That's why we like to show that one.
It's not manned.
Oh God, no, no.
So what kind of, it's fast, what kind of G?
We will peak at about 9 Gs at the burnout of the upper stage at about Mach 6 or 7. Like I said, we get to about 100,000 feet and then we coast to 180, 200 miles and fall back down. So this is where we find them in the desert. We fly out and get them. We track them as far as we can, but they drop below the horizon from the tracking stations. And so we have to go out in the chopper and find it. But this is a good one. This is what it's supposed to look like. I'll show you some others where that didn't happen. And here we are. So this is a Black Hawk now instead of a, where we found it. We break it into 2 pieces now and put them in. So there I am. This was the grad student whose PhD this was. This is the junior grad student who will be launching her PhD in October. And that's a NASA guy. So we load it into the chopper.
You just pick it up.
That's, fortunately, sometimes it lands in worse places, like on the sides of hills, and it's really a pain. And I'll talk about in Australia, it's even, I mean, we've launched from Australia and from Poker Flat in Alaska, it's even worse. Yeah, we just put it in that cradle and get 6 guys on it and shove it in. The whole thing weighs about 1,000 pounds. So it's about 450 to 500 we're lifting. So if it's in rough terrain, that's a bother. And then we fly it back. So you can see that's Nick waving to the photographer. With the payload in there, we fly it back and to the base. So just to do a little science, what this experiment actually did, so these wavelengths here, this is the spectrum of a star. This is where the energy at which hydrogen ionizes. And so this is what we call the extreme ultraviolet, and this green part and the red part is what we measured, which had never been measured before. So in the rockets, because obviously I can't compete with Hubble or the satellites up there, we get 300 seconds in a small mirror. We have to do something no one's ever done before in order to get funded. But the truth is there's a lot of things that have never been done. Usually we have to be either very clever in the design or use some new technology to be able to pull it off, prove that technology, and then get it upgraded to used in satellite programs. Now I'll just mention, like I said, we've launched from Poker Flat. It's a long story why we did that. Normally it's the guys who want to sample, want to fly into an aurora. So they get on the range and they just wait. So we were up there in February. It's because the destruct mechanisms we use in White Sands have been decertified by the Air Force, and NASA hadn't gotten them recertified, and you don't need a destruct in Alaska. So I said, well, we'll go to Alaska and launch. So we were there in February. It was cold. And we were hoping for no aurora the night we launched, because we call that noise, okay, not signal. I'll go back to that in a sec. So this is one of the ones the chute didn't open. There should have been 1 piece. There are 2 pieces. It hit the ground and broke in half. You can sort of see it didn't do well, but this was definitely mine. Now, we didn't find it for a year and a half. It went up in February, but because the chute didn't open, they were searching where if the chute had opened, it had drifted. It had an Iridium phone on board. It was supposed to call with its GPS. It never called. I said it didn't call because the chute didn't open. So we finally searched. Well, the first winter we gave up. The next summer they did a search with phased radar, and we found lots of logs, but not the radar, not the thing. So we offered a $5,000 reward to anybody who came across it, and a hunter found it and got the $5,000.
You have to depend on the missile calling you on an Iridium.
There, because we went over a mountain range, and so we lost, we had loss of signal before the chute opened, so we didn't know if the chute opened. At White Sands, we actually, if everything's working, we have some downrange radar as well, so we can track it pretty low to the ground and have a much better. But here, up here, usually the helical curves they just throw away. Sometimes people launch into you can go a lot higher if you're willing to throw it away into the ocean. But there's only 2 spots, there's only a few spots on the Earth where you can launch and recover, and it's White Sands, Poker, and Australia. So I did want to show real quick video here.
Do you downlink data?
Oh, it's all live, yeah.
Okay.
So we got all the science out of it,
You're
yeah.
not dependent on recovery.
We're not. Some people have such a high data rate that telemetry can't handle it, so it's all being loaded onto solid-state devices on board, and then recovery is, in fact.
Do you do that as well on yours, or you
We just trust the radar. We trust the telemetry. We did have one flight where a TV station in Albuquerque turned on a test during our flight at our frequency, and we lost link. But we inverted the polarization. Somebody was smart and switched the polarization on the system, and we were able to reestablish connection. But that's all real time. It's actually quite exciting. We've also launched from Australia, from Woomera. This is the range we're supposed to launch on. I'll just say we had a guidance failure here, but no destruct, and we missed the 400,000 square miles or whatever it is of range. Now they need destructs down there because of that. But in case you want to know how bad Woomera is, this crowd is old enough to remember The Road Warrior, the movie. It was filmed on the highway from Woomera. That's what it's like. There's nothing there to hit. That's why we didn't need a destruct. So let me see. Since I'm not getting sound, but I'll make a quick show of.
So it's a prohibited area, meaning what?
Well, so it's normally used as a bombing area for the Australian Air Force. Okay, so they set up things and do stuff like that. They were also doing parachute drops when we were there. The paratroopers were practicing drops there and stuff like that. And there's a secret American Air Force, American base just south of there, which no one acknowledges, but the bars are filled at night with guys in American Air Force uniforms. Oh, if you're from Naranja. No, we're just passing through. But it was the downlink for the spy satellites in the days before TDRS. We were told it called Naranja, but of course we may have been being lied to because they didn't even acknowledge its existence, right? So Woomera is a town of 800 with like 14 bars because there's all these soldiers 20 miles down the road. Let me see if I can get this other video to show. So when we were up in Woomera, Ice Road Truckers decided to film us. I'm sorry, no, in Alaska. Sorry. So, but I'll skip ahead to the good part. We didn't make the show, unfortunately, but we did make YouTube. So this is not our payload because we're launching. This is the other payload that was going to launch the day after us because we're on the rail when this is being talked about here. Okay, so it's good. So this lets you see a little bit of what it looks like. So here we are at 46 minutes before. This is the sort of setup. This is what it looks like here. We're tracking it on the radar about where it's supposed to land. That's my program manager. These are all the telemetry stations. That's the actual key to launch it. There I am, real quick. That's all I got in the whole program. Here we are at 50. The countdown going on. This is the radio links, and it's going to launch in just a second. There it goes.
It never aired.
Now you can see these when they go off from 50, 60 miles away. When you're in Las Cruces, which is about 30 miles from the launch site, and you launch in the middle of the night, people who stay up, well, they all know what it is, but it lights up the whole sky.
Do you engender UFO reports, or are they so used to it that?
So when we launched at Hale Bopp, we had one of the campaigns was to view Hale Bopp, and we actually made NBC News, and I was asked about, I said I could neither confirm nor deny that we were actually testing to see if there were alien spacecraft hiding behind it. And the next day, Heaven's Gate happened, if you remember that, so it's my fault. Actually, that part didn't make it on the news, but it said on the side of the "Get them aliens" on the side of the. We go out, we sign the payload and write things on it and stuff like that.
What would you write?
For the Hale Bopp, it said "Get them aliens," because remember there was supposedly an alien spaceship coming to Earth, hiding behind Hale Bopp, and I was supposed to be on the Today Show, and so they did Hale. And then they would add, and I was supposed to be next, going live from White Sands, and I'm talking to the hosts and stuff, and they said, oh, we're going to delay you. There's breaking news. Some bomb had gone off in Israel, and I didn't get on the Today Show. So that was my great chance, but it didn't happen. But I did make NASA TV. Everybody saw that one, I'm sure. Okay, so that's sounding rockets, just to give you a feel. So we do these to test out new technologies. Almost every time we build these rockets, it's for a PhD, for a student. That's how you get into the instrumentation world. You build one of these rockets. That's what I did for my PhD. But we'll move up to Hubble. now 2.4 meters diameter. And I was the principal investigator for the Cosmic Origins Spectrograph, which was done on Servicing Mission 4, that's what SM4. So I'd like to give this timeline so people get an appreciation how long this takes. So AO is an announcement of opportunity in December 1996. NASA put on the web. We are welcoming proposals. They were due on tax day 1997, so we had about 3.5 months to get this together. Servicing Mission 2, when we were writing these proposals, hadn't actually happened. Servicing Mission 1 is when they they put in optics to correct the flaw. Servicing Mission 2 was new instruments. In August 1997, I got the phone call that we'd won, and they also gave me a list of 13 changes they wanted to be reported on by December, including a new design on the channel and all sorts of things. I was very busy. And we had our design review in 2000. When we wrote the proposal, per NASA requirements, we were supposed to launch in 2002, and that slipped to 2004 because they added another instrument, Wide Field Camera 3. While we were waiting, we were actually ready to go. Columbia happened. It burned up, and the Columbia was supposed to be the shuttle dedicated to servicing missions. So we launched in 2006, and then we were canceled because the administrator felt that because if you're in every single remaining Hubble shuttle flight, was going to the space station except for servicing mission 4. And it's in a different orbit, and so if they discovered a hole in the bottom, you can't just fly, there's not enough fuel on board to change the orbit to go to the space station, which is one of the big flaws in gravity. I show that in class to graduates. Say list all the physics errors you can find. It's enormous. But in that movie, if you've seen it, but I still like the movie. So we got canceled in 2004. We actually studied doing it robotically or taking the instruments and building basically Hubble 2 because there was a mirror with the correct shape sitting in the Smithsonian. Unfortunately, I designed all my optics to work with the wrong shape that the Hubble had, so they wouldn't actually have worked with the correct shape. But we still studied that. We got a new NASA administrator and reinstated in 2006. We were scheduled for fall 2008. We were almost there at L-8. The prime computer on board Hubble failed. It has a backup, but we decided we were going to replace the computer. That took a little time. There's a lot of story there. When they called up Goddard, no one could find the spare computer on the ground. There's lots of great stories I could tell. So we slipped out. And so 12 years later, and at least 750,000 actual in-seat flight miles I spent, not frequent flyer miles, multi-millions of those, but 750,000 in the seat. I spent more than a working year in a life in sitting in airplanes and probably equal amount sitting in airports. We did finally launch on May 11th, 2009. So real quick, this is the optical layout of COS. Light comes in from the telescope, from Hubble, goes through a very small hole here, bounces off one of these gratings, which disperses the light and makes a spectrum. And we can choose which one we want onto the detector, and I'll show you pictures of this hardware as we go on. Or one of these is a mirror, and we can send it up to that extra channel they made me design that goes into here. And then we have calibration lamps that can feed light into the system to calibrate it on orbit. That sort of sketch. So when I design these things, when I'm done, all the components magically float in space exactly where they're supposed to be. And I can specify their position, their orientation, and the precision they need to be there. Then the engineers actually make a structure that meets all my requirements. So this is the CAD of the system with a graphite epoxy structure. Here are the lamps, here are those gratings. The detector is back here. And this is the hole that lets the light through. And here's reality coming together, the actual structure. Over at Ball, here we are putting it together. There's the grating with a protective cover on it. It's red. You always know red means remove before flight. Wouldn't want to leave the covers on the optics. The detector is installed in this one, and we're starting to put things together. This is it getting to a much more detailed level. These aren't all correct. There's several miles of cables inside, just to give you an idea, and the allowed air rate on those wires is 0 in terms of pin to pin. So there's a lot of testing that goes on. That's where all the money is spent. It's not on building it, it's testing it. Here it is all put together in its beautiful thing, and this is the latch that will actually connect the Hubble and lock it in.
So you designed it on a table?
I designed it on a drafting board, actually, yes.
Drafting board.
I'm like the last person on earth to use a drafting board instead of CAD. I had a drafting board in my system, and yes, I drew pictures and angles and stuff like that.
Give it to the engineer, and he puts it in a box.
And then I say, this is where everything has to go. Here's where you can't, the light goes here, so you can't have structures in these areas. And these are the baffles I want. So I design all that, but then a mechanical engineer comes in and designs the actual structure to meet my requirements. That's not my job. This is the detector for COS. So this is those microchannel plates. So this is 185 millimeters. It's about that big. They're curved to match the performance. This operates at a voltage of about 6,000 volts. So we don't like to turn it on unless it's in a vacuum. I have somebody in there to give you an idea of the size. This is the supporting electronics for it. These are high voltage. This is Hubble, so we have spare everything. So it only takes one of these to run it, but we have two. This is a pump to keep it at vacuum. This is the door. It has a door to close it and open it. This whole thing weighs about 80 pounds.
How big is that? Is that like a meter?
No, it's about this big.
Okay.
You mentioned a pump to keep it at vacuum. Do you keep it at a harder vacuum than orbit?
No, we can't. I can't achieve that here, but we keep it at a vacuum about 10 to the minus 6 torr. Okay. That's about what the ion pump can maintain it at. So now we ship that down to Kennedy. So now we're at Kennedy, and we're getting ready to get it to go into the shuttle. These are the pictures that are really cool. Here it is going into the carrier that's going to mount into the shuttle.
And by the way, there's only one of these.
Of these? Yeah, there's only one.
You create one.
That's correct.
So if it goes boom,
Then maybe they'll pay me to build another one. I don't know, if I'm lucky.
you get
So-
one shot.
We get one shot. That's with the rockets too. That's why I say testing is so expensive because, if you're making 100 and 2 of them fail, you don't care. But if you're making one, NASA expects it to work. And so that creates a real issue. So here we are in the box. This is what the astronauts will pull it out with when they get on orbit. And this is the high voltage for the pump that will come in to run it when we close the door. So that was disconnected at L-2 days. And then we that goes into this carrier that will go into the shuttle, and we bag that all up, and it goes into this structure. It's called the canister, which mimics the cargo bay of the shuttle. Here's a picture give you an idea of the size. And here it is. We're going to drive it out to the pad with some of my team members. It's a pretty cool truck. The wheels spin 360, so you can drive it sideways. You can go in a circle, forward or backwards. It's pretty cool. It's made in Germany. Somebody came up and said, "Oh, American know-how." I said, "Well, unfortunately, it's made in Germany." Kamag is the company. So here we drive it over. We want it vertical. So there's the infrastructure at Kennedy is really mind-boggling. There's a building whose only function is to take these canisters and make them vertical. So we drive it in, and when it's done, it's vertical. That took about 4 hours. Then we're going to drive it out to the pad. But first I'm going to divert to the Vehicle Assembly Building, the VAB. It covers 13 acres. It's 42 stories tall. It's basically one room inside. It's really, really cool. The lanes of the flag, the stripes of the flag are wider than a highway lane. This was just a good shot that we got with the background. Looks like fake. So meanwhile, the shuttle's getting ready to meet us. So it comes from the Orbital Processing Facility, which is a different building, to the VAB. We're going to pick it up in this crane, 150-ton crane. There it is. And we pick it up. Then we rotate it to vertical and inspect everything. So the whole thing will attach to the rocket at 3 points, 1, 2, 3. This is where the landing gear is. The rest of this are the tiles, the heat-resistant tiles, which have to be inspected. Okay, meanwhile, the rest of it's been put together. So these are the solid rockets. This is the fuel tank, and we have to get the shuttle onto that. This bridge is at floor 13, so we have to lift it up over that and put it down. Yeah, there he is. So one of the design constraints of the shuttle is it had to fit through this gap, which was designed for Apollo. So it goes through just barely, at just the right angle. This operation was very slow, but it does go. So while they were doing that, we had time. We climbed up into the rafters and took this picture. A I'll just emphasize that's a person to give you an idea of the scale here. Okay, so it's going over, it's going to attach onto that. They're going to check all that. I won't go through the problems that occurred during that. I have stories about the problems that occurred in virtually every step. But there it is through finally. And then we're going to wheel it out to the pad. So there's 2 stages, so we only have to open the door halfway. The door was designed for the Saturn V. Okay, the shuttle only needs half the door. This is the mobile launch platform. Beneath it is the crawler. They're 2 separate things. So here we are driving it out to the pad on a special road just for the crawler with these special seashells from some location. And to keep the dust down, we're driving down. When you drove, I was allowed to drive past but not to stop when this operation was going on because I had the right kind of badge. And there were guys with machine guns to make sure I didn't. Okay? I didn't. What? I would have ducked down. I'm not sure they would have shot right away if I'd stayed in it, for example. But so here's the crawler. It has 2 buttons on it for the speeds. One is the tortoise, that's high speed, 2 miles an hour, and the other button has a snail on it, 1 mile an hour. So 1 mile an hour when it's loaded, 2 miles an hour empty. It also has jacks, so when it drives up the hill, it keeps everything level. It's going to pull up into here. It's going to jack up the platform. The platform is going to drop its legs, lock into place. The crawler will then drop down and drive away. So this is what it's going to launch off of. And there it is in place on its legs. And this is where the payload will be installed. Then this will close over and we'll install the payloads into the shuttle. So this is where we're headed to next. Now I mentioned that we got canceled. The solution to the cancellation, since he couldn't go to the space station, was to have a rescue shuttle ready to launch to rescue them in case something went wrong. So that's the rescue shuttle back there. So there's only twice in history there have been 2 shuttles on the pad at the same time. I didn't take this picture. This was a press photo, but there are the 2 shuttles on A and B. And this is the 1,000,000 gallons of water that they dump at the bottom. When you see the big cloud of white smoke that comes out, that's not smoke, that's steam that comes out to dampen the shock wave when they fire up the engines. If there was nothing to carry away the momentum, the shock wave reverting back would destroy the shuttle. It also rocks when they light it, and then when it straightens out, they blow the explosive bolts to go. It's pretty cool. So here we are trying to get this up into the thing at night because it was hot and we didn't want things to get cold, so we still had air conditioning running on it. We got about here and it got stuck. This is the 2008 attempt. Here we are that night. We haven't discovered it's stuck yet, myself, my team. So these 2 guys, this is the head of servicing missions. This is my program manager. The rest of them are CU people who work for me. There we are stuck. They actually rappelled down and guys were jumping up and down on it to try to loosen it up. It finally worked. We got it down, and then the people responsible for the rails blamed the people responsible for the guides and vice versa. But they went out the next day and remachined everything, and the next night it went up just fine. So now it's in there. We opened those doors, and not me, somebody had to go through and clean everything again. Then we would close it over to the shuttle and open the shuttle doors. So here we are. So there's the shuttle. This is the airlock for the astronauts to come through. This is where the payloads go. Here are the various payloads. There are these pins that are going to go in there. These are people that can come out. They're going to rappel down on ropes and guide it in. It's really quite the operation. And it's all on hydraulic lines. So this is a 5-story structure that's all on a crane that can go back and forth and up and down to line everything up the way we want it. It can be reconfigured. I mean, they have a whole building just to fold the parachute. Okay, this is the way it goes. So here we are, all ready to go. So if you ever build your own shuttle, remember that the one on the left is the one with the black band, because they're not the same. They point out. And there we are launching. You've seen that photo. So here we are on orbit. We were replacing CoStar, which was put in as the original fix for the mirror flaw. It wasn't needed anymore because when we went in, now every instrument had the solution to the problem embedded in its instrumentation. So CoStar came out. Unfortunately, our installation occurred in orbital night, so it's a little tricky to see. But there's the instrument. This is Hubble. This is John Grunsfeld down here, making sure he doesn't hit the bottom. This is Drew Feustel. His feet are on the arm. He doesn't actually insert it. He just holds it, and the arm operator, Megan MacArthur, she actually drives him in while they give commands. We then connect. It goes in, it connects. They put a drill on the thing, which closes the clamps and sucks it in. They connect the cables. They back off. This is all we're doing live. We turn it on. We see that all the voltages are good. We turn it off. They go back in and close the doors and call it a night. And then when they go to bed, we ran a full functional in this system.
What was your heart rate?
Pretty high. I was on, so this day I was on console with them in case they had questions. But I couldn't turn on my own mic. Only the mission manager could turn on my mic. But if they wanted to ask me something, I was there. But they didn't. Ours went very smoothly. That's not true about the other wide field camera 3. They couldn't get the bolt out. Stis, they broke the handle off during the repairs. Again, lots and lots of stories about you never hear about.
How does a mistake like that happen?
Well,
Breaks off and
so the helmet would break off because the guy, I won't name the astronaut, stripped the bolts. And we had bolt stripping tools. I mean, we had stripped bolt removal tools, but not for the really large bolts. We thought it would be the small bolts. So it was decided to rip it off. So they had a replica there. We bolted it down to the Torx. We attached a fishing scale to it and pulled to see how hard it took to rip it out. We told him he was strong enough to do it, and sure enough, he just ripped the handle out because we had to do that to get access to fix this.
you're doing that on the ground.
We were doing that on the ground and telling him it's okay to do, yeah. It wasn't me on that because that wasn't my instrument. I wasn't allowed to meddle, but I was there and listening to it all. Well, we had a real problem on day one because we couldn't communicate to Hubble because the Institute had set it to the wrong frequency. And so we ran the whole thing through TDRS that day, and so there was a lot of fuel wasted. And so at the time, it was thought that we were only going to be able to do half of the scheduled activities. And they came to me and said, "We don't need your input, Jim. We know your priority. We don't need your input." But when they figured out and set it to the right frequency, then we were able to do all the activities except the final activity, which was supposed to be to boost the orbit. And that didn't happen, which is why we have issues on reentry. Again, long story. Like I said, I could do a whole class on this. But here I'll give you a little science that this does. For example, this is the early science we did. Here's this is an artist rendering, of course, of a Jupiter-like planet orbiting very close to a star. So we take a and if you know it's happening because this is the brightness of the star as a function of time, and when the planet passes in front, it gets just a little dimmer. See, it's only about 1.5% dimmer, right? Because it's small compared to that. This is a big transit. So here we take a spectrum when the planet is not in front of the star, and a spectrum when the planet is in front of the star, and the difference is because the atmosphere of that planet is absorbing some of that light. So for example, this is in great notation by twice ionized silicon. Chemists would call this silicon 2, and astronomer calls it silicon 3. I won't go into why. But so the red line, this is the flux as a function of wavelength. I know it says velocity of that particular transition. And there's less when the planet's in front because it's being absorbed by the atmosphere. But this silicon that's 3 times ionized exists hotter, so there's none of that there. They're the same. So I just set a temperature of the atmosphere of that planet. Hotter than this, cooler than that. So now I'll move on to biggest, James Webb Space Telescope. 6.5 meter diameter. You'll also hear 6, depends who's trying to brag, because it's not a circle, so it depends whether you measure it from the furthest across the hexagons or the average, or so the longest line you can draw is 6.5 meters. This is cold. This is looking in the infrared. Hubble looks at optical, ultraviolet, and what we call the near infrared. But this is looking at the real infrared, and everything has to be cold. So the mirror has to chill to 40 degrees above absolute zero, and that's done by these sunshades, oriented such that it never sees sunlight and it warms up. Cools down. It all had to deploy. So I like this photo to give people a real sense of the scale. This is not the real James Webb, of course, but this is a 1-to-1 model. At Goddard Space Flight Center, that's Building 8 back there. And this is part of the team that works on James Webb. I remember I went to a meeting, my first meeting at Kennedy for COS. I was told I was in this conference room and we're going to talk about operations at Kennedy. I come in, there's at least 200 people of which I knew one. And I realized, and they all start asking me questions about a document I wrote 6 months ago. We go, oh my God, somebody actually read that document? And I started to appreciate just how huge the scope of running these projects is. Like I said, this is not everyone. It's probably just everyone from that building.
Can you explain the multiple sun shades? I mean, I
Yeah.
get it, but
Why? Okay, so the sun will be on, let me show this picture here. So it's out here in orbit. It orbits in 1 year, which is not obeying the laws, which is why it has to have jets. I mean, it had things on it. The sunshade is always this way, so the telescope itself never sees the sun or the Earth. So the first one gets warm, but the next one doesn't see it, and it gets cool, and then it will radiate, though, its temperature to the next one, to the next one, to the next one, to the next one. So to get it all the way down to 40 Kelvin, 40 degrees above absolute zero for here, you need all these layers. And this has to deploy in space, and this was the scariest part. The first few times they tried to deploy it on the ground, they tore it to shreds. Again, long stories about guys who put the cables through the wrong holes, which is why it didn't work, and
What's it made out of? The shade?
Mylar.
Oh, that's Mylar.
Yeah. It's probably technically Sheldol, which is plated Mylar, okay? You typically
But it's
gold
thin.
plated. Yeah, oh, it's very thin. Weight is a big deal on these things.
But then it's got to unfold.
It has to deploy, unroll, and separate. This is what terrified everyone when we talk about the multiple single point failures in the system. The telescope also is folded up. It has to unfold and deploy as well to fit in the fairing.
Is the focal plane cooled additionally?
The focal, the different detectors are cold to different. MIRI is at 7 Kelvin. That's the coldest, the longest wavelength infrareds. The others are probably at, no, about 40.
the mirror system also had to unfold.
Correct.
and lock into place.
So I'll show it to you folded up. Oh, there it is unfolded, sorry. To give you the size, so it's gold-plated beryllium is what the things are made out of. And so it has to be the right shape at 40 Kelvin, not the right shape at room temperature. So you have to polish it to the wrong shape so that when you cool it down, it winds up in the right shape. Okay? And there's only one way to test that, and that's after you've built the whole thing. Scary. I'll show you that test. So here it is actually in the thermal vacuum chamber where they'll take it down to 40 Kelvin and shine light on it and see if it really meets specifications. So this is a very large vacuum chamber. I'm pretty sure this one's at Goddard. They have several large leads left over from the Apollo program. One of these, which I visited, wasn't at vacuum time. It has an airlock, so you can actually go into the chamber in a spacesuit because they were testing the LEM in there in the Apollo days. And the guys would go in the spacesuit in the vacuum and stuff. So here they are testing the unfolding process with everybody here. It's not designed to work in 1G, it's designed to work in 0G. And so they actually have to put bungee cords on it and stuff to accommodate, to make it think it's at 0G. The motors aren't powerful enough. And here is the mirror folded, so the other halves are folded behind, and this is the secondary, which has to fold down out in front to become the mirror there. And I like this one because I like ones that have people in it so you get an idea of the size we're talking about. And here it is all folded up, ready to go into the actual fairing of the Ariane 5 in the clean room at Goddard. Actually, this might be down at Kourou, I gotta think. So to show you some pictures, so this is the same object taken with James Webb in the infrared and with Hubble in the optical. The big difference is dust scatters regular light, optical light, but wavelengths of light, which are longer in the infrared, ignore objects that are smaller than their wavelength. So in general, long wavelength infrared light sees right through dust. And that's what you're seeing here. You're seeing these stars, these bright stars shown through, but here in Hubble, but way more stars can be seen through the dust here in James Webb because of that. All this scattered starlight, this is all light scattering off dust from the stars here. Well, that's not here in James Webb because that's all optical light. And James Webb sees infrared light. There's a little bit still there. So you get a completely different set of information. So when people say, is it better than Hubble? It's different from Hubble. Its actual limiting resolution is about the same because That's a function of the wavelength and diameter. It gets worse as your wavelengths increase and better as your diameters increase, and the ratio of the wavelength of light you're observing to the diameter of Hubble in James Webb is about the same. Okay? So the actual sharpness of the pictures are about the same, but it's seeing different stuff. And that's why you often get the combines. So here is the same thing again. Here's Hubble. These are the famous pillars of creation on the cover of Time magazine. Here it is in James Webb. So you can see you're seeing way through the hole here and realizing just how big the void is there. And look at all these stars back here that Hubble can't see. You can actually start to see you can actually see the actual star in the tip here. So what these are is, there's a really hot star up here, and there were clouds of dust forming stars here, and the wind from that star is making basically shadows behind these clouds so that these guys are not being blown away by the wind of that star. That's why you get these lanes. But stars are forming here. And so the big question is, will those stars live long enough to form planets around them before all this gets stripped away and just be stars? Or will they actually form planets? And this is part of the stuff we're trying to study. So you see this sort of shape here, a star-forming region with a trail behind it. And what it means is that a really hot, powerful star is up there blasting it.
How do you know what's behind it?
I mean, well, here, I have no idea.
Because of your perspective? Or?
Right, you only get one view. So,
Okay,
yeah.
you can, okay.
So this one I can see because I can see through the dust.
I got it.
But yeah, no, I can't go around and take it from a different,
No,
different
I
angle. Yeah.
just wondered how you could tell that was trailing instead of...
Oh, well, we know the star is up there.
Okay.
It's just not in this picture.
I see.
If we kept it in the picture, it would burn the whole detector out. It's going to be 1,000,000 times brighter than these things. So you leave it out. But in other photos, we know it's there. So this is the galaxy M51, one of the very close nearby super spirals. So here in Hubble, now here's my warning about Hubble pictures. So the colors that are assigned to these are chosen by artists to make them look as cool as possible. Okay? So we do sometimes assign the real colors to the filters for the scientists, but even the scientists, we're just trying to create distinctions. So we take, the cameras are all black and white. So you put a filter in, you take one picture, you only let the red light through. Then you put another filter in, only let the green light through. Then another one, only let the blue light through. Whatever. Some of those filters are broad, some only let little, very specific wavelengths of light through. And then you combine those images, you add colors to each of those things, and when we're releasing for the public, we try to make it look as cool as possible. For the scientists, we try to make the red, so the red here is actually a line of ionized hydrogen and indicates hot new stars, okay? But you can see there's a lot of light here. This is the infrared image. Okay, one, you can see much, much deeper into the center, to the very center of the galaxy, where there's probably 1,000,000 stars there. Okay, here it's completely obscured by the light and the dust. Okay, you can really see that this hole here, I mean, it's in this picture, but here you really see that there's a void without stars. Okay, you're really getting a whole different, and so what happened here is probably some stars exploded here and blew that out. Okay, and this is the combined, but this is why the astronomers get so excited. This picture tells me a whole bunch of stuff. This picture tells me different stuff. I also have X-ray pictures, which tell me something even different. It tells me where the black holes are and things like that. And so we always want pictures through all the wavelengths they've got. We want the ultraviolet, the optical, the infrared, the radio, but it just tells me where the hydrogen is. It's everywhere. That's why we get so excited about making things like this. So this is a planetary nebula. So this is a star that didn't really explode, but sort of puffed its envelope. This is the fate of the sun in approximately 5 billion years from now. We'll already be dead before that, because 5 billion years from now, it'll expand to larger than the Earth's orbit and vaporize the Earth. And about 1 billion years later, it'll do this from a red giant to the phase. But here's the optical picture. This is short wavelength infrared, and long wavelength infrared. So this sees through this. So this is two different instruments on James Webb. This is the near infrared camera, and this is the mid infrared camera. So there's the star left over, the white dwarf, and you can see that it's probably puffed multiple times to create these shells going out. And again, it gives you more information.
So you're looking for all the wavelengths you can get.
Ideally, I'd have a telescope up there that the technologies to measure those wavelengths are different, so I couldn't have one telescope do it all. But they have a whole suite of telescopes simultaneously operating across all the wavelengths. That's the astronomer's dream and the NASA budgeteer's dream as well, because, I mean, James Webb is going to cost, James Webb cost $10 billion, right? It was actually budgeted at $800 million in 2000, but that's another story. So this is just staring at a point in space that they've chosen for a long view, and I'll zoom in on this in just a few minutes. This is James Webb. This is not the same place, but this is what HST sees staring similar to that in optical light. So what you can see, okay, that's a star. You can always tell a star because it has those little, that's scattering off of the arms. Everything that doesn't have that is a galaxy in this picture.
It's the arms
That hold the secondary. Yeah, that hold the secondary.
Everything else is a galaxy.
Everything else is a galaxy.
Made
So,
of planets.
well, of 100 billion stars. And I don't know how many planets. That's a great question. What's the average? How many stars? How many planets per star on average do you get? That's a number. But the number we really want is how many Earths per star do you get, which is what known as Eta Earth, and the Kepler mission was supposed to measure that. It actually is a reasonable. It's not 0. It might be 0.1, as high as 0.1. But these bent ones, and I'll zoom in on this one for you in a second. These are distorted galaxies by the gravitational field. So this is behind this. We know that from the redshift, and it's distorted. Now, I have this also in basically Photoshop, so I can play with it. And I didn't download the full resolution image, because trust me, you don't want me to do that. Which, if you get the TIFF, it's 300 megabytes or whatever. But this is, so I'm going to zoom in on that one so you can see what I'm doing here. So this is a galaxy. You can see the spiral shape and everything, sort of like that. This is so there's a galaxy here. This one's sort of behind it, and the light is being bent by the gravity of this to distort this image. And in some of these even, some of the light will bend this way, and also will bend this way. We can actually see 2 of them with different redshifts because the path length is different, and so the time the light was emitted was different.
Whoa.
So the most famous is the Einstein cross, in which we see 4 of them of the galaxy from that they're coming down in different paths. So these are great. This is how we can see even further in the past, because this actually acts as magnification. So it's brighter than it would be if it were over here. And so we can see to further back in time, because remember, if it's 10 billion light years away, it took 10 billion years for the light to get here. So we can see, so when we look at further back in distance, we're seeing further back in time, and we can track the evolution of the universe that way.
Are one of those wavelengths radio?
Not in this one. This is all James Webb. So you can do this in the radio as well. I mean, you can see mirror image stuff. So radio, you're just opening a whole door, There's a whole course called radio astronomy. So I had to take it for an entire quarter.
Radio can indicate life.
Oh, that kind of radio, yes. Yeah. So most of the radio we do in astronomy is the proton and the electron and the spin in a hydrogen atom flips, and that emits radiation at 21 centimeters. Okay, and that's what like the VLA and all those big, the very large array of telescopes in New Mexico and stuff. Mostly, that's what they're looking for. They're mapping hydrogen in the universe. Because the probability of that is very small, and so the likelihood it gets absorbed between here and the Earth is small, but there's a lot of hydrogen atoms out there, so you can.
Since you mentioned the VLA, do you ever consider like synthetic apertures in space?
Yes, it's extremely difficult. It can be done in the radio, so you have to know the separation of the apertures to a fraction of the wavelength you're operating at.
Like L2, you're pretty stable there.
Well, it's a non-stable orbit, right? So it's like a very shallow hilltop, which is why they have to do station keeping occasionally. So there's a mission called LISA, Laser Interferometric Space Antenna, which is the ESA mission with a triangle of spacecraft that are laser interferometry linked to measure gravitational waves passing across it. They have to measure a micron distortion over 5 million kilometers. It's a rather challenging task. Yes. Oh, LIGO. Yeah. Right, it's measuring those, but over the length of, yeah, it's like, this would be vastly more sensitive, but vastly more difficult. So that was the Hubble one. And this I just think is a cool, hey, what'd you do to me? Okay, so this is a star that apparently has burped multiple times, sending out rings of gas that are now being illuminated. Presumably there's something here in front blocking the view, is why it's not completely symmetric, right? Not that it only burped to one side. That's scattering, yeah, this is either dust emission, I haven't done this myself, or scattered light.
The burps are incredibly regular.
Yes, well, the stars pulse extremely regularly. I mean, Cepheid variables, are in various other kinds of pulses. I know, yeah, I agree, but I just thought it was a cool photo. So, just to wrap up, I'll mention what's coming next. So, every 10 years, approximately, the National Academy of Sciences has a decadal review of astronomy and astrophysics and recommends what should go on in the next decade. So, the first was in 1972, and it recommended the Large Space Telescope, which became the Hubble Space Telescope.
It took 20 years.
It launched in 1990, 18 years. That's about the average. Okay, in 1980 it recommended Chandra. It recommended the AXAF, the Advanced X-ray Astrophysics Facility. So when they give them up, they give them generic names and then name them later. That became Chandra. In 1990 it suggested Certif and Sophia, which became Spitzer and Sophia was just canceled. Certif got warm, so it did. In 2000 it recommended the Next Generation Space Telescope, which became James Webb Space Telescope. In 2010, it recommended WFIRST, the Wide Field Infrared Survey Telescope, which is now the Nancy Grace Roman Telescope, scheduled to launch in 2027, and it's going to do primarily cosmology. Again, I could give a whole lecture on what this does. I served on part of the teams that developed it. And the 2020 decadal, which just recently finished, recommended the Habitable Worlds Observatory, which its primary function is to actually not to find exoplanets. Missions between now and when it flies should find the candidate exoplanets, but it will actually measure them with sufficient precision to detect the presence of life if it's there. That's its goal.
What's the mechanism for detecting life? How do you say
Okay.
there's life in this way?
Okay, there's a whole other lecture for that. There are what we call biosignatures. So you get a spectrum, okay, of the object, and you look for the presence of, for instance, if I saw chlorophyll, I think I'd get I'm done. But I'm not that optimistic. But the standard is to view incompatible gases. Yeah, so if you have both oxygen and methane in the atmosphere, one should have consumed the other, so they must be under continuous production. And on Earth, that's biological processes. There are other ones that people talk about. Now, you'll notice that depending on the astronomer, if they're an infrared astronomer, they feel all the biosignatures are in the infrared. Ultraviolet astronomers feel the best biosignatures are in the ultraviolet, et cetera, et cetera. So this is sort of the Hubble. It was actually proposed in multiple ways. 16 meters in diameter was what they wanted, which is what this picture is. It's currently baselined at 6. It's basically going to be James Webb again, but with all new tech, upgrades, lessons learned, etc. The calls for launch in the 2040s, okay, and a cost exceeding $10 billion.
Is it further away from the sun?
It will be at L2 as well.
It really comes down to a high-res spectrum.
Correct. Well, and highly sensitive, right? Because the signal is going to be faint. The trick, actually, the signal from the planet is actually relatively easy to measure. It's eliminating the confusion from the star. So the starlight has to be suppressed. And that's done either through a coronagraph, internal, or through an external coronagraph, a star shade. This is a raging battle in astronomy right now about which is the best way to do that. There are different designs, different things like that. So this is why they put in the 2040s. They want the 2020s to resolve that problem and say, okay, this is the way we know how to build a telescope. What we don't know how to build is the mechanism to reject the starlight. So if you want to get money from NASA right now, write a proposal to test an alternate technology for coronagraphy that could be usable on Habitable Worlds Observatory, and if they actually decide you're credible, you're going to get funded. But yeah.
So theoretically, you can work it out, but it has to be.
Oh, in theory, they all work great. I can, yeah, on the computer, they work great. Reality,
They're going to have to be testing at some.
correct. And there are people doing that now. So we need to create a contrast ratio of 10 to the 10, i.e. 10 billion to 1 is the contrast ratio we need. You have to reject, the planet is 1/10 billionth the brightness of the scattered starlight. Okay? Okay? So it needs a rejection of 10 billion to 1. And nobody's achieved that yet in the lab, but 10 to the 6 is pretty easy, but pushing beyond that gets very, very tricky.
I mean, Kepler, I guess, but they're identifying a bunch of planets, and there might be special cases where you could do that more easily.
Right, so Kepler found a whole bunch, but they're very far away. And they're so far away it'd be impossible to separate the planet from the star. They use the transit technique. So TESS is up doing surveys of nearby stars right now to identify exoplanets within like 20 parsecs, which then it becomes, you still can't do it yet, but it's at least feasible that you might be able to develop the technology to take care of that. So that's sort of the situation we're in. I wasn't watching my clock. I don't know if I ran over or not. I'm sorry.
I have some layman's questions.
Sure.
Sort of.
That's my last slide, actually.
So the James Webb Space Telescope, I've read sort of things about it. It's making us rethink the Big Bang.
Yes.
Is there anything you can...
I'm not sure I'd say that. So there's two issues that are here. So in the basic Big Bang model, the Big Bang occurs, the universe is uniform soup. It forms the microwave background at about 300,000 years after the Big Bang, 300,000 to 400,000, depends on the cosmology. And we can see that, and it's very, very small. I mean, it fluctuates about a part in 100,000. But from those small fluctuations, matter coalesces, forms stars and galaxies. Our models say there shouldn't be a galaxy to see until a certain amount of time after the Big Bang. If you could look far enough back, you wouldn't see any more galaxies because there wasn't time to them to form. That keeps having to be revised as we keep finding galaxies further and further away. So either they form a lot faster than our models say they can, okay, or we're missing. My personal belief is we have fundamental flaws in cosmology, okay? You have Einstein's equations, and they work great, okay? They explain orbit satellites and Mercury precession and stuff. But when you apply them to the universe as a whole, they don't work very well unless you say, oh, there must be mysterious dark matter, which we can't see, but so it affects gravity but nothing else. I have no idea what this is. Physicists have been searching for it for the last 30 years extensively, are starting to come to the conclusion they should have found it, that phase space is almost closed. Okay? But not only that, I have to create dark energy, which when I was in grad school, that was a term in Einstein's equation, and we always set it to zero because its existence was preposterous. It's energy associated with a vacuum, and when the vacuum increases, there's more energy. Well, what does that even mean? Okay, so we always set it to zero. And I would have been laughed out of the room if I proposed that dark energies, if I wrote a thesis saying dark energy exists, they wouldn't have not given me my PhD back then. But evidence of the expansion rate of history, in order to make the data we have fit the Einstein model, we have to add dark energy and dark matter. And a lot of people, the only reason they're there is to make that equation work. So some people say, well, maybe the problem is the equation. Okay, so we need this generation's or next generation's Einstein, the way Einstein improved on Newton. If that's the situation, I need somebody to improve on Einstein in the same way and resolve the question to the data that exists without invoking things we can't see or find. Yeah, so it used to be felt that was fine. People projected, holes in the periodic table, and people projected elements, and then, oh yeah, they found that element. Yeah, right, it worked great. So they said this is there, but because Einstein's been good for over 100 years now, it's going to take real evidence for anybody to say those equations are not, in fact, correct when applied to the universe. They're certainly right on small-scale experiments we do, even on the size of the galaxies and things like that. But perhaps over the vast distances of cosmology, those equations are inadequate. The same way you don't need general relativity to build a bridge. Newton's equations are fine. You'll get a perfectly good bridge. And so I'm open to the idea that that is going to be coming. Unfortunately, I've been unable to come up with that equation. But there are people who work on what's called modified gravity. Those used to be kooks. Now that's a legitimate theoretical physics arena to try to resolve this equation problem without invoking dark energy.
So now I ask my sort of tongue-in-cheek question. I made the mistake, Nancy and I made the mistake of went to see the movie Everything, Everywhere, All at Once.
Okay, I haven't seen it, but I understand it's simultaneous timelines. Yeah, right.
Multiverse is my next question.
Okay, so when I teach cosmology, I'll ask you this question. I say, cosmology, this is day one, introductory cosmology for non-science majors. This isn't the graduate class. The science of the universe. I said, we're going to define two words today in this first lecture. Science, what does it mean to do science? And second, what is the universe? So could you provide me with a definition of the universe? We all know what it means, but can you give a definition? Okay, until you do so, you can't really do science on that. Okay, so my definition of the universe is everything that can, now or in the future, be measured. Okay, that's my definition of the universe. It doesn't have to be measured now. Okay, so that if the multiverse can actually be traveled between, then it's not a multiverse, it's in our universe. By definition, the universe is uni. If it can't be measured, then I don't care about it. Because by definition, it has no effect. It could exist, there could be 100 multiverses, but if I can't travel to them or measure them or live in them, then why do I care? Okay, so I think the whole word multiverse, if you can travel to them, then that's just part of, it's just the universe is bigger and broader than we understood.
That's the difference between experimentalists who really measure things and experience.
So, final question.
Yeah.
You're retired.
I am retired, yeah.
Aren't you going to miss all this?
Well, I just have to stop teaching.
That's part.
Yeah, yeah, so,
With your career,
yeah,
you started this lecture talking about small rockets and
Yeah.
even sounding rockets. And then
that's what I did first, yeah.
all these features. How did you like working on small rockets that stay up for a minute or whatever and can be launched rapidly, and you get to try all these crazy new things versus
I love it.
dealing with space shuttle launch schedule and NASA and everything. But,
I didn't mind that.
but getting to go to L2, like
Yeah, right. So, yes, the only thing would have been better if they'd made me be a mission specialist to go with it. But,
where, if you could go back, where would you stay?
well, so I didn't stop doing rockets while I was doing COS. The rockets were continuing to run, and before COS, I also built, I didn't mention it, the Far Ultraviolet Spectroscopic Explorer spectrograph, which launched in 1999. And in fact, we built a prototype as a rocket to promote a completely new design for that mission, which was in a lot of trouble because it just couldn't be done in the budget. So we said, I have a clever way, let's prove it works. We did it on a rocket, it worked. We changed the design of the mission. So the rockets are great because I can just, if it's not working, I can put on a glove, reach inside with a screwdriver and fix it, which you can't do that on a Hubble mission, right? I had to get paperwork and stuff like that. But as I'll say, I had people for that, right? I had a team, a large number of engineers, managers. I didn't have to do the budgets. I didn't have to do all that kind of stuff. On the rockets, the student and I do everything, which is great. They don't always work, but there's no substitute for experience in these worlds. And so they continue to fund rockets. We have multiple rocket programs continuing on at CU. I pop in and aid with them, but I don't run them anymore. It's a commitment. But I've done it, yeah, and I proposed some other missions after COS that didn't win, but I was game to do some more smaller missions. They're called Small Explorers, SMEXs. But it's been a great ride. I enjoyed every phase of it. Yeah, so.
Thank you. Don't forget to pay your